So, last lecture we have discussed some of the principles involved in the design of piezoresistive pressure sensors, and today we will take a particular case of polycrystalline silicon called polysilicon piezoresistive pressure sensors, and also we will make use of an approach called SOI, that is silicon on insulator approach. Now, last time what we saw was single crystal piezoresistive pressure sensor, that approach. In the sense, the membrane is made up of single crystal, a square membrane, and the resistors are either implanted resistors or diffused resistors, they are also single crystal. So, in that situation we said that you have to locate these resistors in these positions R 1, R 2, R 3, R 4, that is in the middle of the edge of the membrane. All of them are located in the middle of the edge of the membrane. Two of them are arranged perpendicular to the edge, two of them are arranged parallel to the edge, so as to achieve the maximum sensitivity. We explained it last time. Now, it is very good, gives good sensitivity, etc. There are some problems when you want to use this device in harsh environment like high temperatures. As you raise the temperature, what happens is, if there is a junction, junction becomes leakier and leakier. In other words, junction no longer blocks, is able to block. Here you can see you have got these resistors which are of p type and this membrane is n type. Okay. So, there is a p-n junction here and a p-n junction here, and if the substrate is biased with a plus bias, this junction will be reverse biased. That means, the isolation between these resistors is obtained through this reverse biased junction, which will block the current flow from or connection between R 1 and R 3, R 4 or between the two resistors. But at high temperature, this junction will not be able to block, because the leakage currents will go up. So, that is the limitation of the single crystal piezoresistive resistor approach, though it is very popularly used for higher temperature and harsher environment, which would fail. So, the constraints are poor isolation between the resistors, particularly when you go to high temperature. Temperature coefficient of resistivity of these resistors, that is another problem, it is always positive. So, you need definitely compensation for this TCR and TCS, temperature coefficient of sensitivity. That is, as the temperature goes up, you may use it in applications where temperature is varying. As the temperature varies, the sensitivity will vary. Actually, sensitivity should be only function of pressure, not the temperature. So, that is one of the drawbacks that this particular type of sensor has. And there is restriction on this. If I want to use a p type resistor, which is necessary to get better sensitivity, the membrane must necessarily be n type. So, with all these disadvantages can be overcome if you change the entire style, that is, replace these resistors with the p type or n type, whatever it is, replace these resistors directly on the membrane. Instead of putting them directly on the membrane, realize them on oxide, and when you realize these resistors on oxide, you will see that will turn out to be polycrystalline silicon. Now, let us see what is the problem, what is the situation in the polycrystalline silicon. If you take a polycrystalline silicon, you can see I have plotted here the temperature coefficient of resistivity alpha. Monocrystalline silicon is always positive, okay, quite large. That is one of the problems faced in the monocrystalline silicon because of the temperature dependence of sensitivity. Now, if you take polycrystalline silicon, what is polycrystalline silicon? I just put a simple diagram here. If in the single crystal silicon, from one end, this is a cross section of the silicon, from one end to the other end, you will have one type of orientation, the crystallinity is the arrangement of atoms is same from left hand side to the right hand side. But in a polycrystalline material, it is single crystalline over some region with certain orientation. You have heard about this orientation 1 0 0, 1 1 1 etcetera in the previous lectures. If this is 1 1 1, the next neighboring region may be 1 0 0 or 1 1 0. So, between each of these single crystal regions there is a boundary, and that boundary is called the grain boundary, and each of these are called the grains. So, polycrystalline material will have grain boundary and grain. The grain boundary is a very highly defective region, it is not single crystalline. So, what happens is, if the electrons or the carriers have to move from one region to the other region, it has to cross through this region which is highly defective. So, it gives rise to a problem, in the sense only those electrons which have enough energy can go from this side to this side, because it acts as a barrier. Okay. Now, the property, because of this property, what happens is this polycrystalline silicon has got negative temperature coefficient of resistivity, which is shown here when the doping is low. Grain behaves like the single crystalline, grain boundary behaves with a negative temperature coefficient, because if the temperature is raised, more number of electrons will have energy to climb up this barrier here and go to the other end. That means, electrons can go or get transported from one region to other region rather easily. That will tell you that current flow is easy, that means the resistance is less. That means, temperature coefficient of resistance is negative. That is the meaning of that. Okay. Now, how much is the temperature coefficient of resistance? That is negative, depends upon how much the barrier is. If I keep on adding some dopants more and more, let us, without getting into the mechanism of that, the barrier between these two layers gets reduced. Okay. So, if the barrier becomes 0, that will approach the single crystal, but we do not want that. There will be some barrier which will give the negative temperature coefficient, which is compensated by the positive temperature coefficient of the grain. So, you can see if you keep on increasing the doping, the temperature coefficient of resistivity will keep on becoming less than negative, less negative, and it will approach 0, which would mean that I can adjust the doping in this grain and grain boundary and get a TCR, that is temperature coefficient of resistivity, practically 0 or negligible. That is what you are looking for in polycrystalline. That is the main advantage of using polycrystalline material. So, instead of single crystal resistor, use polycrystalline silicon. So, this is one of the experiments actually carried out by some of our students. This is different doping, this is represent this plot at a particular doping level. Okay. Temperature on x axis, delta rho by rho. If the doping is low, of the order of 10 to the power of 17 or 18, TCR is negative, resistance falls. As you increase the doping, you can see the slope becomes less negative, and at a particular doping of about 5 into 10 to the power of 19 per centimeter cubed, the curve is flat. In the sense, as you vary the temperature from 30 degrees to 90 degrees centigrade, the rho or the resistivity practically does not change. That is the meaning of that. But you can see, if I go to still higher doping, its behavior is almost like that of single crystal. It becomes positive temperature coefficient. That is not what you want. So, you have to adjust the doping. Okay. That doping level is about 5 times 10 to the power of 19 per centimeter cube. Okay. Now, let us see. So, the way you do this polycrystalline resistor is like this. Take a silicon substrate, use bulk micromachining technique to etch the silicon from here, this is a cross section, so that you get a membrane whose thickness is decided by your etching. 10 micron or 15 micron will be the thickness of this membrane, and the dimensions also decided, as we discussed yesterday, by the pressure range that you want to use it. Okay. Now, I grow oxide on that, and on the oxide you realize polysilicon resistor. I have shown 2 of them, there will be 4 actually. So, I have shown 2. So, these 2 resistors are there. you can see there is no connection between this resistor and this resistor, unless you make a deliberate connection outside. So, if I take this resistor, between these two there is oxide. So, the resistivity between these two layers is 10 to the power 14 ohm centimeter, which is insulating layer. So, you get oxide isolation between the two resistors, which will stay in isolation even if you go to temperature like 10 to the power temperature like 500 to 600 degrees centigrade. So, you can use this type of resistors in the form of a bridge and make use of this for realizing pressure sensor, which can operate temperatures like 300 to 500 degrees centigrade very comfortably. Okay. As we have seen, you get oxide isolation here, temperature coefficient of resistivity can be tailored to 0 by adjusting the doping, just now we have seen. Okay. Now, but you can't get anything free, you have to pay for these benefits by something. That is, limitation is that gauge factor is lower than that of single crystal. Gauge factor means delta R by R, change in resistance to the original resistance, divided by strain. In single crystal you may get about 100 to 200 gauge factor, whereas in the polycrystalline silicon it will be something like about 30. So, gauge factor will be low. It will be low, meaning implication is the sensitivity of this device will be lower than that what you get with the single crystal silicon. Does not matter today, because if the sensitivity is low, output voltage will be low for a given pressure, but you can use electronics to amplify the signal. That is not an issue. Okay. Now, this polysilicon is deposited by a technique known as low pressure chemical vapor deposition. What is done is, into a heated furnace you pass silane SiH4 silane gas, it will decompose into silicon and hydrogen, and the silicon will be deposited on this oxide that will turn out to be polycrystalline. This deposition is done at about 620 degrees centigrade. Okay. So, you need 4 resistors to be, what you do is deposit polysilicon everywhere, pattern them, dope them, you get the resistors. We will go through that steps now. Before that, let us see few more things. We said that the gauge factor is lower than that of single crystal, that is depicted by this graph. The gauge factor, longitudinal gauge factor, means actually if I take a resistor like that, okay, if I have a resistor like this, current flows like that, the resistance in this direction is a longitudinal resistance. Okay. Now, the gauge factor, longitudinal gauge factor means change in resistance divided by the resistance when the stress is in that direction, that is a longitudinal gauge factor. That varies from something like about 200 to 70 or so, or 80 to 70 as you increase the doping, in the case of single crystal resistor. In the case of polycrystalline silicon, you can see it is about 30, it is almost constant, that is added benefit. You can go to higher doping, it will remain almost 30. Single crystal you can see, as you increase the doping, the sensitivity will automatically fall. Okay. Now, you take polycrystalline material, subject it to laser annealing, that is heating with laser, then the grain size will become bigger, the gauge factor goes up. If the grain size becomes infinite, it is single crystal. So, larger the grain size, better the gauge factor, that is what is implied by this. What we are sticking down to is this polycrystalline material as deposited, whose grain size will be something like 0.1 to 0.3 micrometers size. So, there will be number of grains on the surface. Gauge factor is low. As I mentioned, nothing to worry about that. The other thing that you have to take care is the gauge factor, longitudinal and transverse, they are different in case of polycrystalline material. In the case of single crystal, we set the longitudinal gauge factor along the 110 direction, it may be 100, and in the transverse direction or perpendicular to that direction, it will be minus 100, which would mean that if I have one resistor which is getting pulled in this along the length of the direction, it will have a gauge factor of 100, that is delta R by R divided by strain will be 100 plus 100. But if it is pulled in the transverse direction, in the case of single crystal, that will be minus 100, that is the gauge factor will be, that means the resistance will fall down, it will be minus delta R by R divided by strain will be 100. Okay. So, in this direction it will increase by a factor x, let us say. In the other direction it will fall by the same factor. Delta R in the plus direction and minus direction will be the same thing. We discussed this, you put them in the opposite arms of the bridge. Now, in the case of polycrystalline material, the gauge factor will be high, maybe about 30 to 40 in the longitudinal direction. In the transverse direction, it is something like minus 10, on an average about 10. So, you can't use the resistance arrangement that is used in single crystal. See, in single crystal, what you have done is, this is the membrane, this is resistor is p type. You have arranged them perpendicular here, they will experience longitudinal strain, and these two you arranged parallel to the edge, they will experience transverse stress. So, delta R positive and delta R negative will be almost same, and you will get very good sensitivity, because R 1 and R 3 will go up, R 2 and R 4 will go down, you get plus there, minus there. So, you get an output of delta R by R divided by input voltage equal to V naught. That is what we have put here. Now, this arrangement has to be modified, because if you arrange like this, R 1 and R 3 will go up if it is polycrystalline material, because longitudinal gauge factor is good, at least 30 to 40. But the change in these resistances R 2 and R 4 will be very small, because gauge factor is small. So, you can't arrange them like that. But what you see here is it is longitudinal tensile stress. If I arrange a resistor such that it experiences longitudinal compressive stress, then you are in business. Because what it means, this curve tells you is longitudinal gauge factor is good, does not matter whether it is tensile or compressive. Okay. So, what the key thing to do here would be arrange the two resistors where it will be subjected to tensile stress longitudinal, arrange other two resistors in locations where it is tensile stress longitudinal, I am sorry, longitudinal stress, but compressive. So, that is what is done in the case of polycrystalline. The arrangement is modified. So, you can see instead of arranging it like this on the membrane, the polycrystalline silicon resistors are arranged in this fashion. This is the membrane, I have shown only one portion of the membrane. These two resistors R 2 and R 4 are perpendicular to the edge. That means, they will be stretched along the direction longitudinally, longitudinal tensile stress will be experienced by R 2 and R 4. That gauge factor is about between 30 and 40, or 30 on average you can say. Now, R 1 and R 3 is the middle of the membrane. If you remember, if I analyze the stress at the center of this membrane along this direction, it will be tensile here, it will be tensile here, but when you go down into the membrane, it will become less tensile, 0. As I approach the center, it will become compressive. Okay. That means, if I locate a resistor, if I lay out a resistors at the center of the membrane in this fashion, that will be compressed in that direction, and that is compressed along the length of this resistor, that is compressive stress. So, if I take a resistor, okay, and if I compress it like that, L will fall, area will increase. Okay. So, resistance will fall. So, compressive tensile stress for p type material, the resistance will fall, and tensile stress, the resistance will increase. So, you have located these piezoresistive polysilicon piezoresistors in regions such that R1, R2 and R4 experience longitudinal tensile stress, gauge factor is about 30, let us say, and R1 and R3 experience longitudinal stress, but compressive, gauge factor is minus 30. So, these R2 and R4 will go up, R1 and R3 will go down by almost same factor. So, that sorts out the problem of the poor sensitivity, the polycrystalline material, if you arrange it in this fashion. So, modify this. Now, these 4 resistors, you can see they are arranged here. The red color, what you see in the bottom here, dotted line is the membrane, okay, and the blue color that you see is the interconnecting metal laid out on the surface of this wafer. Okay. So, these resistors are joined together here by means of metal on the surface of the wafer and then taken to a pad to which wire can be bonded when for packaging the device. So, these two are joined together and taken to the pad. You can see here R1 and R4, R1 and R4, okay. They are joined together here, and I am not showing the pad here. They are joined here, taken out of the membrane to the pad. So, pad is provided somewhere outside the membrane, because onto the pad you will bond the wire. If the pad is on the membrane, if I am bonding the wire onto that, it will puncture the membrane, because this after all about 10 micron thickness. Here it is very thick, maybe 300 micron or 200 micron thickness here. So, pads are located outside the membrane. Okay. So, 4 pads are there, because here it is joined, here is joined. So, 2 pads are used for the power supply, other 2 pads are used for the output. So, since delta R positive and delta R negative are same in magnitude, you will get in the bits on bridge, as we have discussed yesterday in our last lecture, V naught equal to V in into delta R by R. Okay. So, of course, you need to have backside alignment, as we discussed in the previous lecture, that is done by IR mask aligner or backside alignment system. So, that you realize these resistors exactly where the membrane is present. Okay. Now, let me go through this approach. So, all that you need is to have a silicon membrane, on the top of that have oxide, on the top of that realize these resistors. Okay. Now, we will go into one more additional input, that is silicon on insulator approach. Silicon on insulator is used today in integrated circuits. IBM is used it in the mainstream for making the VLSI. So, in many companies they are trying using this, because it has several advantages for making very large scale integrated circuits, because devices can be operated at higher temperatures, higher packing density is possible. I am not getting down into discussion on this, so that is not relevant, but if you can make your sensor also on a silicon on insulator wafer, there is a chance for you to integrate the sensor with the electronics on the same chip. That is our target. That is why we will see how this SOI is made, how the piezoresistor is made on the SOI, and how the integration can be done. That is the topic that we are going to complete today. That is the case study. So, here silicon on insulator, that is SOI, it is said because it is on an insulator. So, here you have got 3 layers: silicon substrate, box, buried oxide. It looks as if this oxide is buried below this silicon layer. Okay. So, that is why it is called box, buried oxide. SOI layer, how to make this? Very simple, I will quickly go through an animation, the process for that. This can be done in laboratory scale, both at IIT Madras and Indian Institute of Science. Our students have done this sort of SOI and fabricated devices on this. Take one wafer, oxidize the wafer, okay, the process to make the SOI layer. Take another wafer, oxidize it and bring them closer together. See this top silicon, bottom silicon, both of them oxide grown on them, put them together and apply pressure, maybe 1 atmosphere pressure or more. You can see this gap between them will close. Bonding, they merge together. Okay. The technique is, initially when you bring them together, the initial bonding takes place because of some OH which is present on the surface. You have to give some chemical treatment, so that the surface becomes hydrophilic, that means water loving. Hydrophobic is water hating. So, we make it hydrophilic by making some chemical treatment. There will be OH molecules, when you bring them together, the initial bonding, pre-bonding will be between silicon, OH, silicon. Then you take it to high temperature, okay, that from the OH the hydrogen comes out and you have silicon, oxygen, silicon, oxygen, silicon, silicon SiO2, that is SiO2 bond. You will have the bonding through the SiO2 itself. Okay, that is the two wafers are bonded. Now, what you do is, I want this top layer to be very thin, etch this protecting back side, etch down. Please note very carefully that portion is etched. See, from here etched complete, that is etch back, bonded and etched back. You call it as SOI sometimes. Okay. Bonded and etched back SOI, silicon on insulator. So, you have got now silicon on layer oxide, two wafers bonded together, top layer reduced to the required thickness. Why do you reduce it to the required thickness? You need for integrated circuits a thin layer there. Also, I can use this for realizing a membrane for making pressure sensor, and membrane thickness will be decided by how much will be the SOI layer thickness. So, if I want 10 micron thick membrane, I will have to reduce this layer to 10 microns. So, originally that must have been 200 micron, I will etch it down, reduce it to 10 micron. Okay. So, you can use this layer to realize the pressure sensor and also electronics. Let us go through further. How the pressure sensor is made on this? So, starting with, you have made this SOI, starting wafer is the silicon on insulator wafer, that is realized, silicon, buried oxide red color, that is SOI layer. Grow oxide on the top of that, because you are going to put resistors on oxide. So, on this SOI layer, grow oxide and then do lithography from the back side, open this oxide, subject it to etching. So, etch it all the way down, this oxide thickness will be just about 0.5 microns. So, this membrane 10 micron, 15 micron depending upon what you want for the membrane. The advantage of this is KOH etching will etch the silicon anisotropically, but its etch rate of oxide is very small. So, when it reaches this oxide, the etching automatically stopped. So, what you have got a membrane here whose thickness is that of the starting SOI layer thickness, that is the merit. Automatically you get a 10 micron thickness if I had a 10 micron thick SOI layer. So, now this SOI layer, you grow oxide on the top of that, it is already there, use this layer now to realize your membrane is realized. Right now, I am showing only how to realize sensor here. On this oxide, deposit polycrystalline silicon by low pressure LP, low pressure chemical vapor deposition. In the sense, in a furnace where the pressure is something like 200 millitorr, you pass silane at keep the furnace at temperature of 620 degree centigrade. The silane decomposes into silicon and hydrogen. That silicon gets deposited on this oxide, and that is polycrystalline. Okay. Now, you pattern this polysilicon by means of lithography. Remember, you want to remove the polysilicon from everywhere except in the 4 red color region here. If this is the membrane, looking at the top view, this is the region where you want to retain that. I have shown the cross section here, so I have shown only 2 here. There are 4. In the cross section, you will see only 2. So, okay, before patterning, you need to introduce boron dopant, which is p type, you introduce dopants to the extent that it brings the temperature coefficient of resistance to 0, that is about 5 into 10 to the power of 19. This doping is done by diffusion or implantation. The temperature and time of diffusion will decide that doping concentration. In implantation, number of dopants which you have implanted will decide that number of dopants, okay, per centimeter cubed. So, once you get that doped by lithography aligned with respect to the bottom membrane, realize this resistor, and once you do that, next step is deposit metal all over, pattern the metal to remove the metal from all regions except in this portion. In the sense, you have these resistors connected together and pads are all provided. With that, your device is ready on the wafer level. Remember, I have shown only one device, but in the full wafer there will be hundreds of such devices side by side. This is repeated, this whatever I am showing here is repeated from all over the wafer in the x and y direction. Okay. You have to separate them out afterwards by dicing. We will see that little later. So, this is the piezoresistive pressure sensor which is complete. Now, the ANSYS simulation. See, now the other thing is, in the previous case we were showing square type membrane. Here we have switched over to the rectangular type of membrane. We have done this because if I make this membrane rectangular instead of square, the stress along this direction, longitudinal direction, becomes more if the length of the membrane is more than the width. Both tensile stress at the edges and compressive stress in the middle, both of them increase for a given pressure. So, what you want is for a given pressure the stress on these resistors should be more. So, you choose this membrane to be rectangular type. For example, if the width is, this is the simulation using a software called ANSYS. For mechanical engineers, they use that software. There are other softwares like Counterware. W is the width, let us say 500 micron, and membrane is 10 micron thickness, and pressure is 3 bar. If the width is equal to length 500 microns, the stress at the edge here, longitudinal stress is about 550 newtons per millimeter square, which is about 500 bar. Okay. That is the transfer stress in that direction, but the longitudinal stress is about 2200 bar, 220 newtons per millimeter square is 2200 bar. Now, if I increase that width to L, if I increase the L and make it double that, width is 500 micron and length is 1000 microns, the stress at this edge, longitudinal stress which was originally 225 becomes almost more than 350. So, this stress is more, that means strain on the resistors will be more, that means the for the given gauge factor delta R by R will be more, that is sensitivity will be more. So, the transfer stress is not increasing much, we are not going to use that. Since length is increased, you will have the stress and the sensitivity will be better. Similarly, if I take the resistor at the center, there the stress is compressive. So, I have shown it as a negative value. As I increase the length from 500 to 1000, the transfer stress goes up from minus 100 to about close to 200. So, if the aspect ratio L by W is 2, it is almost a factor of 2 the stress here, compressive stress. Now, this resistor, it is also longitudinal compressive stress, but stress in the transfer direction we are not looking at, that actually becomes less, which is good, because if there is stress in transfer direction, that will actually reduce the effect of the longitudinal stress. Okay. So, with this gives us the guideline that you have a rectangular membrane rather than a square membrane. So, that the stress in the resistors along the this direction is more both at the edge and at the center. Okay. Now, let us see what will be the impact of that on the burst pressure. The burst pressure is the maximum pressure that you can apply to this membrane, and at that burst when you apply that burst pressure, that is the maximum pressure, the membrane will rupture, because the maximum stress that silicon can withstand is 7 gigapascals, that is 70,000 atmospheres. Okay. So, you can see I take B as the 2B as the length, 2A as the width of the membrane, and the stress will be maximum at this x is equal to A and x equal to minus A. At the smaller width, the stress will be maximum in this direction. So, we have to see by again using the ANSYS simulation, what is seen is if B by A ratio is 1, okay, that is it is 500 and this is 500, you saw that the stress for a given pressure, the stress is less here. That means, to reach the critical pressure or you will reach the critical pressure when you apply higher pressure. Now, if you increase the B to twice that A, the stress here is more. That means, you will reach the rupture stress even with the lower applied pressure. That is the thing what happens. So, for example, 15 micron thick membrane, the rupture stress will be about 220. Now, 220 atmospheres, okay, when the length is length and width are 500 microns. Now, if I take it almost double here, that is width is 500 micron, length is 1000 micron, that is 1 millimeter. At that point, the stress is much higher here for a given pressure. That means, rupture will take place at a lower applied pressure. So, the burst pressure occurs at much earlier it was about 210 bar, or when the ratio is 2 for a 15 micron membrane, it will occur even at about 120 130 bar. So, that means, you must remember that if I design a rectangular membrane, the burst pressure will be low and the usable range goes down. But as I mentioned last time, the usable range is decided by seeing when the nonlinearity sets in, that is output voltage divided by the pressure should be linear. It will stop being linear above certain pressure when the deflection of the membrane, maximum deflection at the center becomes 1/10 of the thickness of the membrane. So, if the membrane thickness is 10 micron, you must see at what point, what pressure the deflection becomes about 1 micron, 1/10 of that. That is the maximum that you can apply. Okay. Now, we will see it soon how it works out. So, these are the guidelines for designing, and all that I have mentioned is the resistors are put on opposite arms of the bridge. See, for example, here they are put on the opposite arms of the bridge, these two will go up, these two will go down. Okay. Okay, here you realize the resistors, these two resistors on the edge are located, they are R1, R2, R3. If I put R1 and R3 are going up because they are longitudinal tensile stress. R2 and R4 they are put on the other opposite arms, they are compressive tensile stress, they are going down by the same amount. Okay. So, as discussed exactly in the same way in our previous discussion on single crystal, because this is going R3, okay, if R3 goes up and R2 goes down, R 3 goes up, R 2 goes down, this voltage go up, and here similarly R 1 goes up and R 4 goes down, this voltage becomes negative, this is positive. Otherwise, if I apply 5 volts, there is 5 volt here, 5 volt here. Now, if this goes up and this if this goes up and this goes down, this will be 5 plus something and this will be 5 minus something. That is why there is a difference voltage plus minus here. So, this is the way they arranged out by considering all the points that we have discussed, and you take this length of the membrane as double the length of width of this membrane, you get best sensitivity. Let us see this. So, with that SOI approach, this has been realized in laboratory. The photograph of the device, I think you can see that. I have put this dotted line here to, this is actually a photograph taken from the top. You cannot see where the membrane is, but to tell you where the membrane is located, I have put this dotted line after taking the photograph. Now, these marks what you see here, they are all the marks which are there to align one layer to other layer, because backside to be aligned with respect to backside membrane is here. I must align these resistors exactly in this location. So, those are done by some of these alignment marks on the wafer. That is the photolithography technique, which you would have discussed already, alignment. Okay. So, you can see these are the resistors. These are at the center, close to center, these are at the edge. And this white, what you see is aluminum wire laid out on this oxide. This is all oxide. This is a resistor on the oxide. These are connected together, taken to this pad where you can bond wire. Similarly, other two are connected to the, taken to the pad, connected together, taken to pad. The symmetry structure is used because you do not want to have difference in the resistance from here to here and from here to here, because otherwise then this is where you apply the voltage and take the voltages. Otherwise, there will be extra resistance which are different from here to here and here to here. So, the R that you talk of will have this resistance of this wire also. So, this length and this length is chosen equal. So, that resistance from here to here and here to here is the same thing. So, that the bridge is exactly balanced. Okay. Now, this is the photograph of this wafer, but this was on a different die, different chip. Instead of aluminum, you will have gold in that. For some reason, we had changed that in one of those runs. This is the silicon. You can see its surface was etched, you can see it is rough, and these are the 4 resistors, and membrane is somewhere here. I have not marked that here. These are the gold wires on the wafer, which is oxide is present, and you can see these pads, you have got the wire is bonded onto that and taken out onto the out of the chip onto the posters. We will see what it is. So, 4 pads which are connected to the, you cannot see it here, here probably you can see better. There are 4 pads, 1, 2, 3, 4, wire is connected to that, to the post, and that post is coming out, that post from here to here it comes, that is this wire which is coming out. All these posts are isolated from each other by insulation around them. I will show you in the different pictures, this is seen much more clearly. Okay. So, this is the packaging, that is you dice that into a wafer, mount the die on this header by some glue, and then do the wire bonding and then put this cap. So, when you put this cap, you put a hole there or put a tube there, so that this can be connected to the, this is a pressure port. You can connect it to the region where you want to measure the pressure. You can even take the tube out, put it into the chamber where you want to measure the pressure, put it into region where you want to measure the pressure. In our case, what we did was, by means of a jig, we connected it to a gas cylinder, so that inside this there is pressure. Okay. So, you can pressurize that, and you can see that when you do the bonding etc., membrane is on the top, the other side is actually sealed. So, only one side sees the pressure. Okay. So, this is the header, this is the die, this is the wire bonding and the wire taken out, and that is a closed one here, and this wire can be gold or aluminum. Okay. Now, quickly going through, this is the output. With this device, apply pressure and apply voltage to the two terminals here like this, measure the output voltage as a function of pressure. So, we can see that for 1 volt input, the output is linear when the membrane is 15 micron and 500 micron width of the membrane, 875 micron length, you get a sensitivity of about 1.8 millivolt per 1 bar pressure change. So, 1 bar pressure change is from here to here. It has gone even up to 10 bar pressure, it has not, its linearity is there. Okay. If I apply larger voltage, you get larger output voltage. There is some offset voltage, that is even when the pressure is 0, there is some output, that is because of some slight difference between the resistors. In practice, you do not have to worry it if you are changing the slope of this, otherwise you will have to compensate this. In a electronic circuit, you can compensate that. Okay. Now, let us see this. See, this is a 15 micron thick membrane. If I make the thickness less 10 micron, you can see that output sensitivity goes up. For 10 volts, it is 69 millivolts, that is for 1 volt, it is 6.9 millivolts. In the previous case, for 1 volt, it was 1.8 millivolts. The sensitivity is better because thickness is smaller, deflection is more. If deflection is more, even at lower pressure, the deflection will become comparable to the thickness. Thickness is 10 micron. So, by the time you apply 3 bar pressure, the deflection will be about 1 micron. So, beyond that point, you get the non-linearity. The output is not linear. It has not gone to burst. It can be operated even up to 6 bar, but linearity will not be there. But if you want to use it without considering the non-linearity, you can use it. If you want linear range or a range of pressure, you must restrict it to about 3 bar. Where it is linear, you get about 69 millivolts per bar for 10 volt input. For 1 volt input, it is about 6.9 millivolts. Okay. So, there is a term called non-linearity which is defined. The non-linearity can be seen like this. If there is a nonlinear characteristic in the pressure sensor and the output maximum pressure is say something like Pm, find out what is the output voltage, join these two lines. If this is actual output characteristics at a given input pressure, see what is the difference between this linear curve and this actual curve, see that difference, okay, V naught I minus this point, that is this second term, that is numerator is this difference divided by that gives you the non-linearity. So, the non-linearity will vary where you are operating. So, for example, here if I am operating this at 6 bar pressure, that is the maximum pressure, maximum output is 450 millivolts for 10 volts. Now, if I am using it at 3 bar pressure, okay, if it were linear, it should have given 250 millivolts output, but because of non-linearity, it is giving about 275. So, the difference between the two, the actual curve and the linear curve is 75 millivolts. 75 millivolts divided by 450 millivolts, it is the full scale output, that is about 1/6. So, the non-linearity will be, in this case, will be about 16%, you can't tolerate that. So, this type of device you can use only up to about 3 bar pressure. If I use 3 bar pressure, the non-linearity all over this range will be less than about 1%. Okay. So, one would recommend this sensor with this thickness and these dimensions to use for only up to about 3 bar. If I want 10 bar, recommend 15 micron thickness with that dimension. So, higher pressure for the same dimension, lateral dimension, membrane diamond to be thicker and thicker. Okay. Now, quickly going through the integration. I can integrate this pressure sensor with the differential amplifier on the same chip with the SOI approach. So, this is a differential amplifier, let me not get down into discussion on that. That is, I can give the output of this pressure sensor connect it to the gate of the MOSFET and take the output at the drain of this MOSFET. You will get output is equal to difference between the two voltages. So, the difference between the two voltages is two gates is 5 volts and 5 volts here 0, you will get 0 output. That is, there is no there is no pressure, all the R's are same for 10 volts input divided equally 5 volts, no output, 0 output. If the output is 5 plus 1 0.1 volts, 5 minus 0.1 volts, 0.2 volts will be output, that will be amplified by the differential gain, that is say 5 volts, like the 5, if you have gain 5, output will be 1 volt. So, you can amplify that depending upon the gain, which is decided by these resistor values. I am not getting down into the design of this in this presentation. Okay. So, this is designed with the certain values of resistors to get a gain of phi using a simulator, and you can see that differential input gets amplified, delta V output versus delta input is linear, the gain is about 4.6 for this device when it is fabricated, descent was about 5, and if I apply same voltage that is the common mode gain is very small. So, you remember common mode rejection ratio should be high for a differential amplifier, this is about 260, okay. 4.6 divided by 0.02, 230. Okay. So, now what I am pointing out is that 15 millimeter thick membrane without amplification gave 18 millivolts per bar for 10 volts. For 1 volt it gave 1.8 millivolt per bar. Okay. Now, I connect an amplifier like this, these two are fabricated separately initially, and if I connect that gain of phi, I get what was originally 18 millivolts, now gets output of 80 millivolts. This was initially run to check the optimization of the two processes, and if I take the sensitivity as a function of temperature, that is almost constant from 30 to 70 degrees centigrade. To show that polycrystalline resistor, which is used as a piezoresistor, worked out very well for higher temperature operation. Okay. Now, you can see this is the SOI approach, silicon on insulator, silicon, oxide, silicon. In this portion of the wafer, fabricate the sensor by etching from bottom, membrane thickness decides the the SOI layer thickness decides the membrane thickness, then you have the resistor here, 4 of them, I have shown only 2 in the cross section. Then the MOSFETs, source, drain and source drain. Resistors are not shown here, you will see in the top view. This is electronics and the pressure sensor together. So, that is to show on this you will have pressure sensor here, Wheatstone bridge, right hand side you will have the electronics. So, pressure sensor on left hand side of the chip, right hand side of the chip you have got the electronics, pressure sensor and the electronics of gain phi. Now, this is to show you how the layout of that will be. See, this is repeated number of times on the wafer using the integrated circuit technology. You have the membrane on this portion, I am showing only one device here. Membrane, the sensor, these are blue is the interconnection using aluminum or gold. You can see the output is connected to the gate of this is a MOSFET, source, drain, gate. So, this output is connected to the gate, the other output is connected to the other gate, and from the drain a resistor comes and out supply, and here also other drain, resistor and the supply, resistor and supply and resistor and supply, like this, from the drain, resistor and supply. Okay. That is getting down to more. What I am trying to point out is you can integrate doing this thing. Now, this is actually the photograph, I deliberately showed you this. On the chip, whatever you saw here is repeated like 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 24 devices are in this area, side by side devices are made on the wafer. If you take a photograph, this is how it looks, and these are all the aluminum that you see the connection. And what you do is you dice the wafer along these lines which are known as the scribe lines, separate out individual devices, okay? And individual die, individual chip has got one pressure sensor and also the electronic circuit. You can just take them out, cut it like this, dice it, and then when if I take a look at this alone, that die looks like this. See, all this together wafer will look like this. If I take dice it virtually by sawing, but a diamond wheel, that is the packaging technique. Okay, cut it in this direction, and then you can take out these individual chips. That is how it looks. This is the membrane portion where the 4 resistors are there, and this is the MOSFET portion where the other there are MOSFET has got 2 resistors which are acting as load. You can see here MOSFET, 2 MOSFET, 3 resistors. That is electronics here. They are here, the resistors. Okay. Now, if I take a look at this die, see what you have done is scribed this or diced this, taken this die, mount it on the header. You can see on the header this is a chip, and you can see the bonding pads here. You can see the wire bonded to this, taken to the other post, and this post and this post are isolated from this insulator. So, there are each one of those pads are connected by means of this wire, very clearly you can see. Okay. That is chip mounted on the header by means of glue, wire bonded onto this bond pad and taken onto this poster. That is where the pressure port is. I can apply pressure to this, test it. That is the test result. You can get without the sensor, without the electronics, with the electronics this gain of 4.5, that to demonstrate that you can use this for realizing this integrated electronics. Okay. Several applications are there which I mentioned earlier, and in summary you can make these devices, integrate them, pressure sensor and accelerometer and electronics together. Okay. You can use these references where some of the articles written by me, a review article on pressure sensor, then some of my students on this integrated sensor, papers have been published on this. You can see those things. Thank you very much.